calculating the derivative in terms of the parameter. Hello, everyone. In our previous sections, we established the theoretical basis for parametric differentiation, ensuring we understood the underlying principles of how these variables interact. Now we are moving into this subsection, where we will shift our focus toward the practical application of this method, essentially, how to actually perform the calculations. To set the stage, imagine we have two variables, x and y, but instead of y being a direct function of x, both are defined in terms of a third variable, which we call t, or the parameter. In these cases, when we calculate the derivative of y with respect to x, our final result will typically be expressed as a function of this parameter t. You might wonder why we use this specific approach. The advantage here is that it allows us to find the slope of a curve without the need to eliminate the parameter first. In many mathematical problems, trying to rearrange the equations to express y solely in terms of x can be algebraically tedious, or in some instances, completely impossible. The step-by-step process. Now that we have established the theoretical foundation in the previous slide, let us move on to the practical application. To calculate the derivative of a function given in parametric form, you should follow these three systematic steps. First, we begin with step 1. Differentiate x with respect to t. In this step, you take the equation where x is defined as a function of t and find its derivative with respect to the parameter t. This process gives us the rate of change of x relative to t, which we denote as dx by dt. Next, we move to step 2. Differentiate y with respect to t. Similarly, you take the equation where y is defined as a function of t and find its derivative with respect to the parameter t. This provides us with the rate of change of y relative to t, denoted as dy by dt. Finally, we reach step 3. Combine the results using the parametric formula. Here, we apply the chain rule to find the derivative of y with respect to x. The formula is as follows: dy by dx equals dy by dt divided by dx by dt. One important detail to remember is to ensure that dx by dt does not equal 0, as division by 0 is undefined. Once you have performed this division, the final result is usually simplified algebraically and left expressed in terms of the parameter t. In the next few slides, we will put this three-step process into practice with some illustrative examples to see exactly how this works in different scenarios. Illustrative examples. Now that we have established the theoretical three-step process, let us apply it to a practical problem. Please look at example 1, which deals with basic algebraic parametric equations. Our goal here is to find the derivative of y with respect to x, given that x equals a t squared and y equals 2 a t, where it is treated as a constant. Following the systematic approach we discussed in the previous slide, we begin with step 1, finding the derivative of x with respect to the parameter t. Given that x equals a t squared, we apply the power rule for differentiation. The derivative of a t squared with respect to t is 2 a t, therefore, dx over dt equals 2 a t. Now we move to step 2, finding the derivative of y with respect to t. Our equation for y is 2 a t. Since 2 is a constant coefficient of t, the derivative is simply the constant itself. Thus, dy over dt equals 2a. Finally, we proceed to step 3, where we combine these two results using the parametric formula. As we learned, the derivative of y with respect to x is found by dividing the derivative of y over t by the derivative of x over t, substituting our calculated values into this formula. We get 2a divided by 2 a t. To reach the most concise form, we simplify the expression by canceling the common term, 2a, from both the numerator and the denominator. This leaves us with a final result of 1 over t. So, the derivative of y with respect to x is 1 over t. This result is expressed in terms of the parameter t, which avoids the need to eliminate the parameter algebraically. In the next slide, we will see how this same logic is applied to a real-world physics problem involving trigonometric functions. Illustrative examples continued. Now that we have covered a basic algebraic example, let us move on to a real-world application involving particle motion to see how these concepts apply in physics. Imagine a particle moving along an elliptical path. In this scenario, the position of the particle is represented by two parametric equations, x equals a cosine theta and y equals b sine theta. In these equations, a and b represent the semi-major and semi-minor axes of the ellipse, while theta serves as our parameter, representing the angle. Our goal here is to find the slope of the tangent to the path, which is the derivative of y with respect to x at any point theta. To solve this, we will apply the same three-step systematic process we established in the previous slides. First, we find the derivative of x with respect to theta. Given that x equals a cosine theta, differentiating this with respect to theta gives us a times negative sine theta, which simplifies to negative a sine theta. Second, we find the derivative of y with respect to theta. Since y equals b sine theta, its derivative with respect to theta is simply b cosine theta. Finally, we calculate the derivative of y with respect to x by combining our previous two results. Using the parametric formula, we divide the derivative of y by the derivative of x. This gives us the fraction b cosine theta divided by negative a sine theta. To reach the most concise form, we can apply a trigonometric identity. Since cosine theta divided by sine theta is equal to cotangent theta, the expression simplifies to negative b over a, multiplied by cotangent theta. As you can see, whether the equations are simple polynomials or trigonometric functions, the method remains the same. In the next slide, we will discuss some common mistakes to avoid so that you can ensure your calculations are accurate. Common mistakes to avoid. Now that we have walked through the practical examples, it is crucial to discuss some common pitfalls to ensure you avoid them in your calculations. First, let's address the issue of inverting the ratio. A frequent error is calculating the derivative of x with respect to t divided by the derivative of y with respect to t, instead of the correct order. Always remember that since our goal is to find the derivative of y with respect to x, the derivative of y with respect to t must always be placed in the numerator. Secondly, be careful not to ignore the parameter. Some students attempt to differentiate y with respect to x directly, bypassing the parameter t entirely. However, if your equations are provided in the form of x equals f of t and y equals g of t, you must first differentiate both variables with respect to t before combining them using the parametric formula. Finally, watch out for simplification errors. Once you have expressed the derivative of y with respect to x as a fraction of two derivatives, ensure that you perform your algebraic simplifications carefully. This includes canceling out common constants or applying trigonometric identities, much like we did in the elliptical path example, to reach the most concise and professional form of the answer. Keeping these points in mind will help you avoid unnecessary mistakes. Now, let us move to the final slide to summarize the key takeaways of this lesson. Key takeaways. To wrap up our lesson, let us review the key takeaways to ensure you have a solid grasp of the concept. First, remember that parametric differentiation is the specific method we use when both x and y are not defined in terms of each other, but are instead both functions of a third variable, which we call the parameter, typically denoted as t. As we discussed in the step-by-step process and applied in our examples, the calculation follows a consistent three-step sequence. First, you find the derivative of x with respect to t, then you find the derivative of y with respect to t, and finally, you divide the latter by the former. It is important to note that your final result for the derivative of y with respect to x will typically be expressed in terms of the parameter, whether that is t or, as we saw in the physics example involving the elliptical path, the angle theta. Lastly, always keep in mind that the formula, where di over dx equals di over dt divided by dx over dt, is not an arbitrary rule, but is actually a direct application of the chain rule.